So a new unit, Unit 6, is on two other types of functions, exponential and logarithmic functions. Up until now, we've really looked at two types of functions. We looked at um, polynomial functions. And remember, polynomial functions were something like this, where all the exponents were nice whole numbers. We didn't have negative exponents. We also looked at rational functions, and rational functions were fractions with variables in the denominator. So that was the type where we had to be careful if we had to throw numbers out that x couldn't be. Those were the type of graphs that had asymptotes when they were graphed. So in this first section, we're going to add a third function to our list called the exponential function. And we're going to practice evaluating them. We're going to practice graphing them. We're going to look at a specific case with e. And the last part of today's lesson will be like the application side of things. So, what is an exponential function? Well, it's a function whose equations contain a variable in the exponent. Up until now, all of our functions, we've had numbers as the exponents. Exponential functions will have variables as their exponents. So what do I mean by this? Well, it could be something like this. F of x equals 5 raised to the x. Notice a variable is the exponent. So that's what makes this exponential. It could also be something like this guy. Again, notice there's a variable as the exponent. That's what makes it exponential. So let's just see if we can work with these to begin with. The exponential function f of x equals, and then it gives me the function, models the average, whoops, hang on just a second here, models the average amount spent, f of x, in dollars at a shopping mall after x hours. What is the average amount spent to the nearest dollar after 4 hours? So after 4 hours. So what does this want me to do? What is the average amount spent after 4 hours? And it said x was the number of hours. So I should just have to substitute 4 in. So what I'm basically finding is f of 4. So this is something I would want you to try in the calculator. You should be able to enter this whole entire thing at once. If you want to do it in pieces, then I would do 1.56 raised to the fourth and then times 42.2. What we should get, and we're going to round to the nearest dollar, so the whole number, is about $250. So what does that answer mean? Well, after 4 hours, that is the average amount spent at a shopping mall. Is that you? I don't know. Maybe you spend more, maybe you spend less. All right, so let's look at graphically what happens with these guys. There are two types of exponential functions. We can either have a growth or a decay. If you have a growth function, they will be in the form f of x equals a raised to the x. Notice we have a variable as the exponent. And what I mean by a can be any number as long as it's greater than 1. That is what's going to make it a growth. What you're going to see on these graphs to begin with, there is going to be a horizontal asymptote going through 0. So there's a horizontal asymptote through y equals 0. Why is that? Well, that means the graph, we're not going to touch that red line. Well, why can't it become 0? Well, the reason is there is no number I can substitute in for x to make this entire thing come out to 0. And you might say, well, duh, put in 0. Well, if I put 0 in for x, remember anything to the 0 power is 1. There is no number I can substitute in for x and get 0 out. That's why we're going to have a horizontal asymptote at 0. What ends up happening, the y-intercept of this graph will be at 1. And I kind of just told you why it's at 1. When I put 0 in for x, anything to the 0 power is 1, so I got 1 out. And what ends up happening, here's what the graph looks like. It's really close to the asymptote, and it starts getting exponentially bigger and bigger and bigger. An example of exponential growth, think of like people getting sick. Maybe on day 1, 2 people are sick. And then on day 2, 4 people are sick. And then on day 3, 8 people are sick. And then 16 people are sick. And then 32 people are sick. It just keeps getting bigger and bigger and bigger. If I asked you to tell me the domain of this graph, remember domain, we're looking left and right. So how far left does the graph go? Well, it keeps going left. How far right does the graph go? Well, it keeps going right. So my domain is negative infinity to infinity, everything. That will always be the domain for exponential functions. Always. That will always be the domain. Now the range can be slightly different depending on what we're dealing with. So the range, remember we're looking from bottom to top. How far down does this graph go? What is the lowest point or the lowest y value that this graph gets to go? Well, it's getting closer and closer and closer to 0. So we're going to start with 0. And how high up does the graph go? Well, it keeps going. So we would say infinity. And now the question is, what would I put with 0, a parenthesis or a bracket? Well, because of the asymptote at 0, I'm never actually going to reach it. I'm just going to get closer and closer and closer. So we'd want a parenthesis. Where is the asymptote? Well, we said it's going through 0, but make sure when you write the asymptote that it's y equals 0. It's an entire line. Okay, what about the x-intercept? Where does it cross the x-axis? I'll tell you, because of that asymptote, it doesn't. It doesn't get to cross the x-intercept. What about the y-intercept? Well, we already said when we put 0 in, we got 1 out. And we're not going to worry about the end behavior for these guys. Okay, now let's look at the other one. The exponential decay graphs do just the opposite, so there's still going to be a horizontal asymptote at y equals 0. And what makes these guys decay instead of growth, for their form, they're still going to be a to the x, but what makes them decay, that a value, my base number, has to be between 0 and 1. So it was growth if a was bigger than 1. It's decay if it's between 0 and 1. And you might say, well, why don't they just say less than 1? Well, they're avoiding the negatives because if the negatives appear, that's going to be one of our transformations. Remember, the negatives reflect it. So that's why we're just not going to worry about the negatives. So it turns out the y-intercept is still going to be up at 1 because if I put 0 in, anything to the 0 power is 1. But what the decay graphs do, they get less and less and less and less, so closer and closer to 0. So a lot of the times, this type of problem comes in if they're trying to figure out, okay, how many resources will we have left over a given amount of time? Or if they're trying to figure out if they find an artifact, how old is it? They can look at, based on the elements that are left, how fast are they breaking down? at something called half-life, which we will look at in the last unit of this lesson. So let's do the domain. How far left does it go? Well, it keeps going to the left. How far right does it go? Well, it keeps going to the right. So my domain is negative infinity to infinity. Again, that will always be the domain for exponential functions. The range, we're thinking bottom to top. How far down does this graph go? Well, it gets closer and closer to 0. How high up does it go? Infinity. It keeps going. The asymptote is still y equals 0. There is still not an x-intercept because I'm not going to touch the x-axis, but I do have a y-intercept through 1. And we're not going to worry about the end behavior. So let's try some examples with numbers here. Graph the function, and then we're going to list all of these characteristics. We're not going to do the end behavior. So f of x equals 2 to the x. What I ask my students to do first is I ask them, is this going to be exponential growth or is it going to be decay? Well, if we look at the base number of 2, 2 is bigger than 1. So this is going to be a growth graph. So what that automatically tells me right off the start, I know when it gets graphed, it's going to do this. It's going to be growing. So I'm going to keep that in mind. I already know without seeing the graph, this is my domain. I do not need to see the graph to do that. That is always the domain of exponential functions. Now notice on this graph, there's no transformations. There's not like a +7. It's not going to go up 7. It's not going to go down. It's not going to go left or right. So what that tells me, I know the asymptote is still going to be at y equals 0. So I'm going to draw that in, y equals 0. If I want to know what the y-intercept is, if I put 0 in for x, anything to the 0 power is 1. So the y-intercept, when I put 0 in for x, I got 1 out. And since this is a growth graph, I can fill it in. Oh, that was bad. Okay, not perfect. I'll allow these to be rough sketches, and it will actually be easier to graph these on MyMathLab. Notice, because of that asymptote right on the x-axis, I'm not going to touch the x-axis, so there's not going to be an intercept for the x. What's the range? Well, how far down does this graph go? 0. And how high up? Infinity. Now, one thing I want to point out, because there will be some questions about this, if I asked you to fill out a table, let's just quick see if we can do that. If we made a table, let's say we wanted more points to plot. If I asked you to use these 5 x values, let's see what we get. So if I plug -2 in for x, I would get 2 to the -2. Now it's been a while, but remember what I said about negative exponents. If I want to turn it positive, I move it to the other side of the fraction. So 2 to the -2 would actually become 1 over 2 squared. So I would get out 1 over 4. If I did 2 to the -1, I'd move it, and it'd become 2 to the +1, but on the bottom. So I'd get 1 over 2. If I put 0 in, well, we know that's just 1. If I put 1 in, 2 to the first is just 2. And if I put 2 in, I'd get 4. These could be additional points if you wanted to plot them. So notice my graph isn't the best because like 1, 2 should be on the graph. I almost hit it. 2, 4 should be on the graph, so my graph was a bit sloppy. But I will expect you to know how to evaluate a table by plugging things in. So we got to remember about negative exponents. Let's try the next one. Graph the function and describe the domain range. We're not going to do end behavior. So I would ask first, is this growth or decay? And we should say this is a decay graph because my base number, 1/2, is smaller than 1. So I know when it comes time to graph, it's going to do this. It's going to be falling. Because this graph is not moving up or down, there's no transformations out back, I know the asymptote is still going to be through y equals 0. I'm also going to fill in my domain. Okay, let's get the y-intercept next. So if I put 0 in for x, anything to the 0 power is 1. So the y-intercept, when I put 0 in for x, I still get 1 out. I'm going to draw in the graph now so I know it's a decay graph, and I got to pass through my intercept. So something like that. I know I'm not going to have an x-intercept because my asymptote is right on 0, so I'm not going to touch the x-axis. And the range. How far down does this graph get to go? Well, it gets closer and closer to 0. How high up? Infinity. And there is my graph. Let's try the next one. Now this one's a little bit trickier. First off, is this growth or decay? We should say growth because my base number is bigger than 1. Now, we got to be careful though. Notice on this one, there is this -3 out back. What kind of a transformation is that? When it was out back and it was being subtracted, what did that do to our graph? You should say this means the graph is going to actually move down 3. All right, so we have to take that into account. Let's think about this. If the whole graph is going to move down 3, then my asymptote, instead of being at 0, it's now going to be down at -3 because the entire graph is moving down 3. So now it's going to be at y equals -3. I wonder what the y-intercept would be. Watch what happens when I put 0 in for x. 2 to the 0 is 1. 1 minus 3 is -2. So my y-intercept is now at -2. And here's a pattern if you haven't spotted it. The y-intercept will always be 1 above the horizontal asymptote. The y-intercept will always be 1 above the horizontal asymptote. And so now, since this is a growth graph, I'm just going to draw it in here. Okay, so I know my domain is -infinity to infinity. Now be careful with the range. How far down does my graph get to go this time? What does it get closer and closer to? You should say -3. And then how high up does it go? Well, it keeps going to infinity. Now, I'll tell you there is an x-intercept, but you might say, oh, it's 2. Well, remember, I kind of just free-handed this graph in, so it's not necessarily exactly 2. With our skills that we have currently, we don't quite have enough knowledge to find the x-intercept yet. So I'm going to make a note. There is an x-intercept, but for now I'm not going to make you find it. And you won't have to worry about finding it on my math lab. We will find it eventually, but right now we're not quite ready to find it. It's actually a decimal. It's not a pretty number. Okay, moving on. Let's quick review transformations. So describe the transformations if f of x equals 4 to the x is the parent function. So remember, when I say parent function, think of this guy as the original. And now I want to know on these 4 problems, what would these transformations be doing to the graph? So this first one, the only thing that's different is a negative has appeared out front. You might have to look back at your transformation notes, but if a negative appears out front, that was an an x-axis reflection. So it would flip upside down. Let's look at the next one. Notice on the next one there's a minus 3 with the x, and on the one after that there's a minus 3 out back. These do two very different things. Let's do this one over here, the minus 3 out back. We know that means down 3. But what about if the minus 3 is up with the x? Remember I said if it was with the x, that's going to be your left or right movement, but I said those were liars. So that should actually mean right 3. The whole graph would move right 3 because it's with the x. And the last one, notice the negative is up with the x. So that is a y-axis reflection. Okay, so we have not seen the end of the transformations. We will see them come back this unit. The next piece of information is one of the goofier things in math, and whenever students first get introduced to this, they think I'm crazy. Well, most think I'm crazy before this, but this solidifies the fact that they think I'm crazy. The number e, that phrase by itself just sounds ridiculous. E is a number? What? Yes, it is. The number e is considered to be an irrational number. So what do I mean by that? Well, remember we said if a number is rational, it can be written as a fraction, or as a decimal, it will either stop or it will repeat itself eventually. So where this number comes from, back in the day, they had an expression that looked like this. And they noticed this expression as they started plugging numbers in for x. So like if they plugged 1 in, they got 2 out. If they plugged 10 in, they got 2.59 out. If they plugged 100 in, they got 2.7 out. If they plugged 1,000 in, they got 2.718 out. They noticed as they continued to substitute values in for x, the numbers that were coming out started getting closer and closer and closer to this weird decimal, this 2.7 business. And it turns out the higher you go, the more decimal places start tacking on, and they became really intrigued by this number, very much like what happened with pi. The gentleman that this number is named after, there's his name, and people always want to say Euler. It's actually pronounced Euler. It's German. So that's why it's given the letter E. It's named after this gentleman. So the number E is like 2.71828, blah, blah, blah. It just keeps going, but it hasn't repeated itself yet. For our purposes in this class, if I ask you, hey, what is the number E equal to? I would like you to know that it's roughly 2.72. That's what I want you to be familiar with. Kind of like if I said, hey, what's the value of pi? You would tell me, oh, 3.14. I want you to know that E is 2.72. So let's try working with it here. The exponential function, and then they give me the function, models the gray wolf population of the Western Great Lakes X years after 1978. According to the model, what was the gray wolf population rounded to the nearest whole number in 2014? So I'm going to take my function, but I don't want to substitute 2014 in because it told me I'm dealing with X years after 1978. So first we need to subtract 2014 minus 1978. I need to figure out how many years have passed. And it turns out it's been 36 years. So that's what I want to substitute in. So now when you do this in the calculator, you can enter this in all at once. When we're doing this in the calculator, most scientific calculators will have an E button, and I'd prefer you to use the E button. It'll help keep the answer more exact. On most calculators, the E button can be found. You should see an LN button. So a lot of calculators, you'll see an LN button, and then right above it is an e to the x. So on most calculators, to do e to the x, you first have to hit your second button and then the ln button, and usually it'll bring up this then. So like if I was typing this in, I would do 1145 times, and then I would do second ln, and I'd get my e raised to the, and then I would type my values and hit enter. If you do this correctly, rounding to the whole number, you should get 3,689, and what does this represent? Well, it's the number of wolves. By the way, anytime e appears, this is an example of exponential growth. Why is e considered exponential growth? Well, we know e is 2.72, and that's bigger than 1, so that's a growth function. We're gaining. The last examples that I want to do today are some application problems. So one of the bigger applications is compound interest. When you're talking about interest, a very broad definition is how much are you paying for the use of someone else's money? So there's two ways that we can deal with interest. We can talk about it compounded n times per year. This is an example of a formula that you will not have to memorize. It will be given to you. You just have to know how to use it. So it's P times the quantity 1 plus R over N, that's an R over N, raised to the N times T. And what these variables mean, P is called the principal. And when we're talking about money, the principal is like your initial amount. How much money did you start with? T is going to be the time involved. And for this equation to work, it needs to be in years because it is n times per year. So the time has to be in years. So like if I was dealing with 6 months, I would actually refer to it as 0.5 years. I want to do it in terms of years. R is your rate, your interest rate, and we need to make sure it's not a percent. So if they give it to me as a percent, I need to convert it out of a percent. And then N is the number of times that we are compounding per year. What do I mean by that? Think of it as the number of times that it's going to build on itself in a year. The other type of equation that we have is compounded continuously. What if it's just constantly building on itself? The formula looks almost identical, except this entire middle chunk here, you're going to see E. And then it's raised to the R times T. Why does E replace that? Well, it's kind of coming from what I just told you. This function is the number E. So it's kind of like it's replacing that middle piece. A lot of my students will refer to this equation as PERT. They just know it as PERT. But again, you don't have to memorize these. So let's try 2 examples and be done. So Christi, I don't know if that's how you say it, but that's how I'm going to say it, invests $300 in an account with a 6% interest rate. What will her account be after 20 years if the interest is compounded? So I kind of have 3 problems here. So what happens if it's compounded semi-annually? Let's first figure out what would N be. If I'm building on it semi-annually, how many times a year is that? That's twice a year. So N is going to be 2. So let's see if we can substitute in. So what would I substitute in for my principal? $300. That's my initial amount. And then I have 1 plus. Now R, 6% is my interest rate, but I need to change that out of a percent. So to change it out of a percent, you can either divide by 100 or just picture moving your decimal 2 places left. So 6% as a decimal is 0.06. That's what I want to use in my setup. And then we want to divide by n, so 2. And then we're raised to the n times t, so 2 times, and my time involved was 20 years. So this is what we would want to evaluate in the calculator. And if you evaluate it correctly in the calculator, and I would try doing this, and if you can't do this, you need to let me know so we can figure out how you're typing it in wrong. You should get $978.61. Notice this is higher than what she started with, which it should be. If it's lower, then she needs to find a new bank, because that's not what should be happening. We're building on it. Let's try the next one. What happens if I leave everything the same, but this time I'm compounding monthly? How many times a year would that be if I'm building on it monthly? Well, we should say n is now going to be 12 times a year. So when I set this up, everything else is not changing, but anywhere I had an n, I'm now using a 12. So this answer, in theory, should be bigger than the first one because I'm building on it more often. If we enter this in, you should get $993.06. So even bigger. Look at the next one. What if I want to build on it or I want to compound it daily? How many times in a year would that happen? Should say n is now 365. So this answer should be bigger than the previous two because I'm building on it even more often. So if I substitute in, everything's going to stay the same, except my n's are now going to be 365. And you should get $995.94. And the last example, same setup, so we're still putting $300 in, still have a 6% interest rate, but here's the kicker. Compounded continuously, so we're going to constantly build on it. If there are no other deposits or withdrawals, what will be her balance after 20 years? So everything is staying the same, but since I'm building on it continuously, that's kind of the kicker that I'm going to use PERT, because I'm building on it continuously. So if I substitute in, I have my 300 principal, E, which is a number, it's that 2.72, R is 0.06, and my time is 20. So that's what I would want you to try entering in. Use the E button. Don't use 2.72. We want to keep our answer as exact as possible. And if you do this correctly, you should get $996.04. If you are having trouble using the calculator to get any of these answers, please make sure you let me know so we can get it fixed.